Hello, my name is Abderraouf FARES and I am an assistant professor at the USHB University. And welcome to the course Silicon Photonics. In the next few minutes, I'd like to describe what we will be doing for the next semester. We will talk about the motivation for Silicon Photonics, then we will go into the course logistics in terms of the resources, the time commitments, and so on. And then I'm going to talk about the design fabricate cycle, including the modeling, the fabrication, and the automated test, and finally the data analysis. So, this course is specifically designed for the Master's 2 students specializing in telecommunication systems. We assume that the students have a following prior knowledge in electromagnetic theory, optical communication fundamentals, and basic semiconductor physics. This course is ideal for students aiming to have a transition into integrated photonics, research, or industry, gain a hands-on experience with design, simulation, and analysis tools used in silicon photonics, and understand the design to fabrication workflow of what we call the PICs, or the photonic integrated circuits. Then, this course is kindly sponsored by several design tools vendors. Numerical Solutions is providing two of its packages, namely numerical modes and numerical interconnects. These are used for component and circuits modeling respectively. These tools run on your own computer. MathWorks is providing MATLAB. MATLAB actually is a very popular mathematics tool, and there are a lot of other examples on the internet and in the textbooks on how to model optical components and circuits. MATLAB not only runs on your computer but also within the web browser. You will see many activities through that use MATLAB. Mentor Graphics is providing PI6, a tool for creating the chip layout. This tool is run on Linux, and Mentor is also providing us with a virtual cloud environment where you can access these tools. They are also providing Calibre, which we use to do design checking and to merge your designs for fabrication. For the layout, we are using the excellent open source K layout program, and you can also use Python and other tools of your choice for the data analysis. So, the course is graded as follows. 50% is based on the online questions, which are done using the web browser. 10% of your grade will be during the design review, where your colleagues will assign your points based on the specific rubric. Your peers will check things like whether your waveguides are properly connected. 20% is given to data analysis. Specifically, my objective is for you to show me that your model agrees with your experimental data. And of course, there is an error in the measurements, which, as we'll see, is primarily a result of the manufacturing variability. So your model needs to take this into account, and the last 20% will be your final design report. So let's take a look at the course schedule. We will illustrate this as a cycle instead of as a linear progression. The reason that the designer typically go through the design cycle multiple times. So after the course, I will invite you to continue to iterate and improve upon your design. In the first week, we will start with modern optical components such as waveguides. Then we will proceed with the circuit modeling and design. Next, we will create a mask layout. The following week, we will have a design review. During this week, you can keep improving upon your layout based on the feedback you get from your peers. We will have a final submission deadline, at which point the designs get sent for fabrication. While your designs are being fabricated, you will learn about fabrication and manufacturing challenges. Once the chips are back, we will automated test for your design, and in the final weeks of the course, if all goes well, and assuming none of the equipment is broken, you will get your experimental results back and perform your analysis, and that will complete the design cycle. Thank you so much for your attention.